Good afternoon, everybody. Let's get started. For announcements, we will have our first exam next Wednesday, February 12th. I will send out an announcement on what the content is and what the rules are for that. Basically, there's going to be an exam assignment issued via Canvas, and you'll work the exam. That will be during the regular class period. 4:40 to 5:30, but then you'll have an extra 30 minutes grace period to submit your exam in case you have any troubles submitting the exam to Canvas. So you'll download it, work the exam, upload a scan to Canvas. I will send out a Canvas announcement about that. So look for that in the next few days. Take a look at quiz 3 that is due coming up, I think, on Wednesday. That has to do with node voltages. You've got a lot of quizzes coming up early in the semester, and that's because they're really the fundamentals that you need to know to go on to the more complex material later in the semester. So if you have any questions about those, stop by office hours, and we can talk about that. My office hours will be right after class, so stop by, stick around on this Zoom session, and we can talk after class. So last time we were talking about node voltages and node voltage analysis. And we didn't really start node voltage analysis. I gave you some of the prerequisites for that, but node voltages were a voltage between a node and a reference node, right? Like V1 and V2 here are node voltages. And then I mentioned you can solve for other circuit variables when you have all the node voltages. So if only you had a way to solve for all of the node voltages within a circuit, then you're one or two steps away from solving for power and for currents and for voltages across resistors that aren't node voltages. So I showed you this slide, and the point of the slide, well, there were 2 points. One was, once you have a couple node voltages, let's suppose you know V1 and V2, or you've calculated those, then you're one step away from calculating IX or IY, or you're one step away from calculating Vx or Vy, okay? And then you can calculate power from voltage and current, or voltage and resistance, or current and resistance. But the second point I wanted to make here is the currents from one node to another node are what we're going to use in node voltage analysis. So I want to point this out here. You're going to have two node voltages like V1 and V2, and you're going to quickly, with this pattern, write a term in a KCL equation that is the current. So if you want the current, for example, you want to write a term that's the current going from V1 to V2, that's going to be V1 minus V2 over R1. If you want to write a term in your KCL equation that is the current going from V2 to V1, that's V2 minus V1 over R1. IX is negative IY, so you can have currents pointed in the opposite direction, just one is the negative of the other. But so you're going to see this pattern come up when I do the node voltage analysis problem next on the whiteboard. You're going to see this pattern show up, and this is what I'm using right here. Okay. All right, so let's move away from the PowerPoint slides and move over to the whiteboard, and we will talk about an example problem. We'll talk about node voltage analysis. All right, so this is going to be node voltage analysis. So let's work this, or let's teach this, let's learn this with an example circuit. So that circuit's going to look like this. And it's pretty much going to be, well, I think it is, that circuit we've been talking about with a current source and a few resistors. So if ever you can't see what I'm writing on the whiteboard, shout it out, let me know. We'll fix the focus or fix something, fix my writing so that you can see everything I'm writing here. But I like to work these problems in real time so you can see, kind of how long they take to solve and what all the steps are. Okay, so I have this circuit. Let's suppose you know all of the resistor values. So this is resistor R1, this is resistor R2, R3, R4, R5. So all those values are known. It might be 10 ohms, 20 ohms, 50 ohms, whatever. They're all known. And you have a current source, I sub S, and that current is known. It might be 2 amps or negative 4 amps, whatever the value is, but all of these values are known. Right? And then let's suppose that I define a reference node. So I'm going to put the reference node here. That means this whole bottom node is a reference against which we're comparing the voltages of the node, of each node, the node voltages. Okay. So let's define a few node voltages, 3 node voltages here. So I have 4 nodes in this circuit. I can define 3 reference or 3 node voltages once I've defined that reference node. So this is going to be V1, V2, and V3. Okay, so I've just written those node voltages next to their respective nodes. Okay, and so our job is, given we know all the resistances, we know the current source, we've defined a reference node, it's been given to you. I want to find these 3 node voltages, and that's what node voltage analysis does. Node voltage analysis is a systematic process. It's a method to find V1, V2, V3, or all of the node voltages in the circuit. Okay, so how do we do that? Well, there's a pretty straightforward way to define the process or write down the process of node voltage analysis. You do this. You write KCL at every non-reference node. Okay, and that's it. That's that right there is the whole process of node voltage analysis. And then the trick is actually doing it. So let's go through an example of how to do this. Remember, I know all the resistor values. I know IS. We want to find V1, V2, and V3. So first, let's recognize I have to write a KCL equation at each of the non-reference nodes. So I'm going to have 3 KCL equations. That's good because I have 3 unknown node voltages. I'll have 3 equations and 3 unknowns. And when you do this process, these equations will be linearly independent, and you'll be able to solve these equations simultaneously and get numeric answers for V1, V2, and V3 if you have all the resistor values and the current value. Okay, so let's write KCL1. KCL1 I'm defining as the Kirchhoff's current law equation that I'm going to write at the node corresponding to V1. Okay. So remember that a node is the entire connection between circuit elements, right? So that's node 1. And I want to sum the currents leaving that node. So whenever I do node voltage analysis, and I recommend this, I'm going to use the form of KCL that is this. Sum the currents leaving the node, set that sum equal to 0. If you do that every time, you'll be consistent. I think you'll have better results. So what I'm going to do, by better results, I mean fewer mistakes. What I'm going to do is I'm going to sum that current plus that current plus that current. Those are three currents leaving node 1. Right? Okay. So let's do this. Let's start with this current. What's the current going from node 1 to node 2? Sometimes I'll call that node V1 to node V2. What's the current leaving from 1 to 2 through that resistor? Well, we just derived that on the prior slide, ending last class, beginning of this class. And so the current going from V1 to V2 is V1 minus V2 over R2, right? That's that term we looked at on the slide. Okay, so that's that term. The second term I'll write is the current leaving from left to right through the current source. Well, that's IS, right? And then sum that with the current going from V1 down to the reference node. All right, so the current going down through R1. Okay, that's going to be this node voltage, V1, minus this node voltage divided by R1. Well, what's the node voltage of the reference node? It's voltage compared to itself, so that is 0 volts. So the node voltage of the reference node is 0 volts. So this node voltage minus this node voltage is this. V1 minus 0 over R1, right, is the current going down. So the current going down through R1 is V1 minus 0 over R1. So I've summed all of the currents leaving that node, node 1, and I set that sum equal to 0. Okay, so you look at what I have here. I have an unknown V1, an unknown V2. All the rest of the terms are known, or the variables. R2, IS, R1, they're all known. I'm going to wind up solving simultaneous equations here. And so what I'm going to do is kind of simplify this a little bit. So I have some coefficient times V1 times a coefficient times V1 plus a coefficient times V2 plus a coefficient times V3 equals some number. Let me show you what I mean here. So the coefficient of, let's see, R1, or I'm sorry, V1, the coefficient of V1 is 1 over R1. So 1 over R1 plus 1 over R2 V1. So, right, 1 over R1 times V1 plus 1 over R2 times V1 is this. So that's the term, that's the coefficient of V1. The coefficient of V2 is minus 1 over R2 times V2. And I'm going to move IS over to the other side. So minus IS. Okay. So you can expand this out and you can see that these two equations are equivalent. Okay, so someone asks in the chat, are we counting the currents leaving V1 as positive? And if they were going in, they would have been negative. So here, I don't know if this current is actually positive or negative. I don't know. Numerically, I have no idea. V1 and V2, if V1 is greater than V2, that's a positive current. If V1 is less than V2, that's a negative current. It just doesn't matter. So what we do know is that the current, if you go back to that last slide, the current going from V1 to V2 in that direction is V1 minus V2 over R2. You know, why is that? Because the voltage with that polarity across R2 is V1 minus V2. And the current going in that direction into the positive side of the resistor there for that reference polarity, you know, I'm defining that current. So I use this voltage with this polarity. So by Ohm's law, V1 minus V2 over R2 is the current going from left to right, right? So I'll show you when we get to the currents for V2 that we're going to have a current going in the opposite direction. But let's just let's like not care what numerically these values are, and write the other two equations. Now notice here I have a number times v1 plus a number times v2 minus a number times v2 equals a number. So you have, a nice equation here with v1 and v2 are your variables you're trying to find. The coefficient of v3 is 0 in this equation, but you're going to have a set of linearly independent equations that you can solve here. But let's continue on. Let's now write the KCL equation for this node, node 2. Remember, the node is the entire connection between circuit elements. So V2 applies to that whole middle red node there. So let's write KCL2. Okay, so now again, I use the form of the equation where I'm going, or the form of KCL, where I sum currents leaving the node. So I'm going to sum that current plus that current plus that current. Okay. Now you say, wait a minute, I assumed the current was going the other way right here. Well, this current is -1 times this current. It'll work out. I'll show you how that works out. Okay, so let's just write this. So for KCL2, the current going from V2 to V1, or node 2 to node 1, is this node voltage minus this node voltage over R2. So that's going to be V2 minus V1 over R2. All right. And again, you say, well, wait a minute, you just assumed current was going left to right. Now you're assuming current's going right to left. Well, one of these is -1 times the other. Look at these two terms right here. V1 minus V2 over R2, V2 minus V1 over R2, right? This is the same current going in the opposite direction. So you multiply this in the upper right times -1, and you get this in the lower left. So it's the same current, but just be consistent. So I'm using the form of KCL where I sum the currents leaving the node I'm concentrating on. I sum all those currents leaving, and I set the sum equal to 0. Okay. Okay, so I'm summing these three currents. I have the current going right to left through R2. Let's get the current going left to right through R4. Okay, the current going left to right is V2 minus V3 over R4. Okay, so that's the current going left to right through R4. The current going down through R3 is V2 minus 0 over R3. I've summed those three terms in the KCL equation, set that sum equal to 0. Okay, and remember, you know what the R values are, and so the only unknowns are V1, V2, V3 here. And so let me write, again, a coefficient times V1 plus a coefficient times V2 plus coefficient times V3 equals something. So let's see, V1 is going to be its coefficient minus 1 over R2 times V1. It's this term here. V2 is going to have 1 over R2, 1 over R3, 1 over R4. It's V2. And then the coefficient of V3 is minus 1 over R4 times V3. And that equals, I have no other constant in there, I have 0. Okay, so that's my second of three equations that I need. I have a number times V1 plus a number times V2 plus a number times V3 equals 0. Okay, let's continue on with KCL number 3. So here, concentrating on this this node here. So I'm going to sum the currents leaving that node, that current plus that current plus that current. Okay. Let's do that. Let's see. Okay, the current going right to left through R4 is V3 minus V1 over R4, right? Oh, V1, V2, I'm mixing up my numbers here. V3 minus V2 over R4, V3 minus V2 over R4. And you say, wait a minute, right? We had opposite direction currents here. Well, if you look at this term, this is -1 times that term. So we're consistent here. So that's the current going through R4. The current going through the current source, right? Leaving V3, leaving node 3 through the current source is negative IS. And the current going down through R5 is V3 minus 0 over R5. So you can see how that pattern that I showed on the last slide, on that previous slide, it comes in handy because it's really easy to write a current term for your KCL equation. It's easy to write that term when you have node voltages defined on either side of a resistor. Okay, so I've summed these three. That equals 0. Let's rearrange this into something a little more pleasant to put in a matrix or an equation solver. So minus 1 over R4 V2 plus, let's see, we have an R4 and R5. 1 over R4 plus 1 over R5. That's times V3 equals, move IS to the other side. Get IS. Okay. So I have a number times V2 plus a number times V3 equals a number. I have three unknowns, V1, V2, V3 in these three equations. And so I can solve these using whatever I want. Okay. Let's see. Someone asks, is the source current negative now because the arrow in the source indicates the real direction? Well, yeah, this current source, if I were to draw the current, in this current source, this is IS, this is IS, right? That's IS. And in this last equation, I was trying to figure out, well, what's the current leaving V3? And that current leaving V3 is, put some space here, is negative IS. So if IS goes left to right, negative IS goes right to left. And I wanted the current leaving that node, not entering that node. Yep. All right. So now we're at the point in solving this problem, right? You have to solve three equations, three unknowns, get the answers. It doesn't matter to me how you solve these equations. I'm going to show you what I do. I use a matrix solver. I just write a linear algebra equation with a matrix, and I solve. So you can do that. You can use an equation solver, whatever you want. Let me give myself a little more space here. So let me show you what I do. I'm going to express these three equations in a matrix form. So let's do this. So let's see, I'm going to put the coefficients of V1, V2, V3 like this. So this is R1 over R1 plus 1 over R2. Okay, that's the coefficient of V1. Coefficient of V2 is negative 1 over R2. Right? Coefficient of V3 is 0. So I'm writing all these out as a matrix. So that's this equation. This equation, so the coefficient of V1 minus 1 over R2. This is 1 over R2 plus 1 over R3 plus 1 over R4, negative 1 over R4. And finally, 0 minus 1 over R4, 1 over R4 plus 1 over R5. Right, so that's my matrix times V1, V2, V3 equals minus IS, 0, IS. So this is why I formatted those equations in this way, so I could have this matrix of coefficients times V1, V2, V3 equals, these are numbers. So in this matrix, we know all the R values. This is just a 3 by 3 matrix of numbers times the variables I'm looking for equals, and these are just numbers, right? You know what IS is. And so this is actually expressed in this form. We call this matrix here I'm going to put cap G for that G matrix. It looks like a conductance, right? You have all these reciprocals of resistances. So G times V, this V column vector here, equals I, right? So it's G times V equals I. That looks a lot like Ohm's law, doesn't it? Right? You have conductance times voltage equals current. That looks a lot like Ohm's law. We're solving for V. So what I can do is I can say V equals the inverse of G times I. Okay. So that's how I solve this. I put a matrix of numbers in my calculator or in MATLAB, works in MATLAB. I invert it. I multiply it by this column matrix here, and I get an answer. I get a column matrix with 3 numbers that are my V1, V2, V3. Okay. And you're welcome to do this. I find this pretty easy to do if you have MATLAB, if you have a calculator that solves matrix equations. You're also welcome to put these equations into an equation solver on your calculator or whatever you have, whatever software you have that can solve simultaneous linear equations. But I sort of stepped away from node voltage analysis. Node voltage analysis really is writing the 3 KCL equations and then solve those equations. Okay. Okay. Someone asks, what happens if you have a voltage source instead of a current source? Well, there's a technique called supernodes that I would show you. We're not going to have problems that involve supernodes, which involve making a node, one big node where, let's suppose this were a voltage source. I would use nodes on either side and form this supernode. Um, that's one way to handle it. We're not going to do problems like that, but what you will see is for example, if I replace R5, pretend I replaced R5 with a voltage source that is just 5 volts, right? Make that a 5-volt source. So now instead of R5, I have a 5-volt source. Well, since the 5 volts is directly connected between ground and V3, you can immediately write V3 equals 5 volts, right? Because V3 is the voltage between this node and ground. If I've put a voltage source in there, then V3 is the voltage between this node and ground, which is 5 volts, right? Enforced by that voltage source there. So that's how you could handle that voltage source. So you will see problems in this class where there's a voltage source connected between ground and some other node, and then you know what that node voltage is because there's a voltage source between ground and that node. So, but I'm not going to give you any super node problems. Okay. Someone says, how would you solve a matrix like this without MATLAB? I'm kind of confused on how you would do this without a calculator or a program. Yeah, I mean, you unless you're in linear algebra class doing this by hand. I I have a calculator, and if you have many of your scientific calculators can handle matrices, so you can do this with a calculator. You can also put this into MATLAB and just define G as this matrix. You know, put in G to the power of -1 times I, the column matrix, and you'll get V as a column matrix. So, and you can use MATLAB on your exam for your homework for your quizzes. So yes, you would use MATLAB or your calculator. Okay, will there ever be a case where the current arrows are pre-assigned for us at each resistor, or can we rely on this method? So there, I'll say that um, whenever you're doing node voltage analysis, maybe forget about what arrows are defined, what reference directions are defined for you, and just do the analysis. Now, there might be a problem that says, oh, find the current IX, right? Find the current IX. You don't have to use that symbol IX in your equations, right? You don't have to use it. But at the end of the problem, once you know your node voltages, then you can say, I know V1, I know V2, so I can calculate IX. IX is V2 minus V1 over R2. So in this case, you have to use that reference direction if it's given to you to calculate that value. But when you're doing your node voltage analysis, you could just ignore the symbol IX there. Okay. Yeah, Gauss elimination. You could do that. You could, you know, that's fine if you want to do it by hand. I'd recommend you. I think you all have access to MATLAB. This is pretty easy to put into MATLAB and solve if you don't have an equation or a matrix solver in your calculator. Just start up MATLAB and put this in. Okay. All right. So that is node voltage analysis. Again, it's summarized by, well, you have node voltages defined, you have a reference node defined. Use this process, write KCL at every non-reference node, and solve those equations. So that's the typical node voltage analysis problem. If there's a voltage source in your problem, then you can see, well, in this case, if R5 were a 5-volt source, V3 would be V3 equals 5 volts. That's one of your equations. And then you write KCL for the other two nodes. Okay, so I think give this a shot with your homework problems. There's also, check out the practice problems linked to Canvas. You'll see a heading called practice problems. Those are problems I created that start easy and get a little harder, but there are complete explanations of one or more node voltage problems and node voltage analysis problems there. So take a look at that. Okay. All right, so we talked about node voltages. We talked about node voltage analysis. I want to move on to a new topic called Thevenin equivalent circuits. Let me bring that up now. Okay. So Thevenin equivalent circuits, when you pronounce that, it's kind of a funny word, Thevenin. Thevenin equivalent circuits are useful circuits that are used to model or represent what is a more complex circuit. So, for example, let's suppose you have an audio amplifier to which you want to connect a speaker, and you want to figure out what's the power delivered to that speaker. And speakers within a range of audio frequencies act mostly like a resistance. So it's like delivering power to a resistor. But if you have speakers that are maybe one's 16 ohm, one's 8 ohm, one's 4 ohm, whatever, you want to know how much power is delivered to each one of those. You would think, wow, I need to know that entire schematic of the audio amplifier to know what's the voltage, what's the current, what's the power delivered to that speaker. Well, in in reality, you don't. You can calculate the Thevenin equivalent of that audio amplifier. You don't have to worry about all the transistors and the op amps and the integrated circuits and the capacitors. You don't have to worry about that, because if that audio amplifier acts like a circuit with sources and resistors, you can create a Thevenin equivalent circuit. So it's a very simple way to model a more complex circuit. You can use you can model the output of antennas. You can model the output of a video output of some kind of device that outputs video, like a satellite receiver or other video devices that you connect to your TV. So Thevenin equivalent circuits are a great way to model a circuit. And then we're going to talk about maximum power transfer. Oftentimes you want to know, how do I get maximum power transfer from maybe a weak source like an antenna or a sensor to a device that's trying to sense that signal, and get the most power. Why do you want the most power? Because that maximizes the signal to noise ratio, that maximizes the quality of the signal that you're going to be able to decode or demodulate. Okay, so this is a pretty important topic practically. Okay, but let's back up a little bit. So let's talk about V versus I of linear resistive circuits. So voltage versus current of linear resistive circuits. And here's what I mean by a linear resistive circuit. It is any circuit, any linear circuit with resistors and sources, and those sources can be independent and dependent. Okay, so it doesn't matter. There are also other circuits that behave as if they're only resistors and sources. They have transistors in them, they have capacitors in them. They can behave like a circuit with resistors and sources. But let's just right now, when you see a problem in the textbook or your homework, it's going to be, if it's a Thevenin equivalent problem, it's going to be a linear circuit with resistors and sources. Okay, so if I take this circuit, right, this linear circuit, linear resistive circuit, and I expose two terminals, and that's where I'm going to connect something else. Let's suppose I connect a resistor. I'm going to call that a load resistor. Okay, you're typically delivering power from this circuit, like it's an amplifier, to this load resistor, which might be a resistor, might be a speaker, but that's the load. Okay, so I'm connecting a resistor between the two output terminals of this linear resistive circuit. And so I want to take a look at what is the relationship between voltage, current, and this resistor value. So let's define a voltage across that load resistor called R sub L, or the voltage is V sub L. The current going down through that load resistor is I sub L. So what I'm going to do, I'm going to create a plot. I'm going to create a plot of voltage versus current as I change this resistance R sub L. I'm going to see how this circuit on the left behaves, or what's the output voltage and current, as I change the load resistance. So that plot is going to look like this. Load voltage versus load current, V sub L versus I sub L. So if I have some resistor value, 100 ohms or 1,000 ohms, whatever, I put that resistor, connect it to terminals A and B, and I'm going to have some value for current and some value for voltage. You can measure it, you can calculate it, do whatever, but that's a dot on this plot. Okay, So it's going to be some value. Now, we can move that resistor value to its extremes. I could have that resistor value go all the way up to infinity or all the way down to zero or anywhere between zero and infinity. So that's what we're going to look at on this plot. If I take that resistor value and I move that resistance value all the way to infinity, that's like an open circuit, I'm going to have no current flowing, right? If I have an open circuit, R equals infinity, I have no current flowing. So IL equals 0 amps when R sub L is infinity. That's an open circuit. Infinite resistance is called an open circuit. Well, we're going to give that dot on this plot and that voltage corresponding to that load voltage a special name. It's going to be called VOC, the open circuit voltage. All right. So that's VOC, the open circuit voltage when RL is infinity, when I have an open circuit. I can take that load resistance, right, this load resistance, and turn it all the way down. I can make it 0 ohms. Instead of infinity, I make it 0. So now I have a short. I have a short circuit. A short circuit is if you short between two terminals, it means you're applying 0 resistance or as close as you can get to that between two terminals. If you use a wire and you put it across two terminals, that's a short. So if I put a wire here, I'm going to have 0 volts between A and B, right? There are 0 volts between a node and itself. I've just taken A and B. I created one node out of A and B because I put a wire there. So I'm going to have 0 volts. So that's where this is. So voltage is 0. And that's when the resistance is 0 ohms. And that's the short circuit. We give a special name to this current, I sub L. We call it the short circuit current. So when you short the terminals, the short circuit current flows. And a neat thing happens when you change the resistance between 0 and infinity. You get a straight line. So if you have a linear circuit with resistors and sources, and those sources can be independent, they can be dependent. They just can't have like squared values in there. They have to be linear. That's a linear resistive circuit. If you connect a resistor to the output terminals and you change that resistance, you're going to see this linear relationship, right? V versus I is going to be this line, okay, with that slope. So you can write an equation for that line, and that equation will describe the relationship between voltage and current. And here it is, V sub L equals VOC, right? That's the y-intercept there, the voltage axis intercept, plus the slope, which is negative VOC over ISC, right? This slope here is negative VOC over ISC times I sub L, right? So that's just the equation of that line. Okay. Okay, so the importance of this is I can relate voltage across the load to current through the load based on the resistance value, or as I change the resistance using this equation. All right. So let's figure out how to use that to determine an equivalent circuit. We're going to call that the Thévenin equivalent circuit. We'll get there. So if I have this is what I had on the last slide. This is the resistor. This is the changing the resistance causes the voltage and current to change like this. And we want to find an equivalent simple circuit for multiple reasons. We might want to analyze this complicated circuit multiple times. So let's make a simple circuit, an equivalent simple circuit. Or if we want to characterize the circuit, you don't want to show someone the details of the circuit, or it doesn't really matter. So you just give them a simple model of the circuit. So we want to find an equivalent simple circuit. But from the load's perspective, from this resistor's perspective, what does equivalent mean? From the load's perspective, any circuit in this blue box, any circuit that has the same VL versus IL relationship will be equivalent, right? If I take a resistor and it's a variable resistor that changes from 0 to infinity, and I get the same VL versus IL equation, that same line, then it's equivalent. I can't tell the difference. I could put both circuits the original circuit and the equivalent circuit inside a box, exposed to terminals, I wouldn't be able to tell the difference from the load's perspective. So let's define a variable that represents VOC over ISC. V over I sure looks like a resistance, right? That just feels like a resistance in Ohm's law. And so we're going to call it a resistance. We're going to call VOC over ISC R sub T. Okay. So I take R sub T and I plug it in to this equation, and I get this equation. Right? That resistance, it's R sub T because it's going to be called the Thévenin resistance. Okay, so these two equations are the same. I just substituted RT equals VOC over ISC. Okay, and I did that for a reason. I'll show you. But now let's draw a circuit that has the same VL versus IL relationship as this, more complicated circuit. Okay, let's derive the relationship V versus I for an equivalent circuit. We want a circuit that does this because we know this is what the original more complicated circuit does. And I'm going to throw a circuit out there. I'm going to say, let's try this circuit. Okay, so the circuit that I've replaced that blue box with is the circuit to the left of these terminals. So I've taken that blue box with resistors and sources, and I've replaced it with a source and a resistor in series. I took that complicated circuit, I just replaced it with this. Let's see if I get the same VL versus IL relationship. Okay, so how are we going to do that? Well, let's first recognize that the voltage across RT is IL times RT by Ohm's law. I have IL going this way, left to right. The voltage there is IL times RT. Now I have all these equations defined around this, or all these voltages defined around this single loop. Let's write a KVL equation. So I'm going to say start at the bottom, minus VOC plus ILRT plus VL back to the starting point equals 0. So I get this. Okay. And if I rearrange this a little bit, I get VL equals VOC minus RTIL, which is a match, right? So these two equations match, which means any load connected to either that original circuit or the simple circuit with a source and a resistor, they both see the same thing from the perspective of the load. The circuit behaves the same. So we'll define RT to be this Thévenin resistance, the single resistance that I just kind of made up here and then showed that it worked. We're calling that the Thévenin resistance. Okay, and that's that VOC over ISC value that we defined on the previous slide. All right, and then we're going to define VT to be VOC. We're just, it's the same thing. We're just renaming VOC. VOC was the open circuit voltage, the voltage that was present when you didn't connect anything to the terminals. We're going to call that the Thévenin voltage. Okay. All right. So so that's what we're going to call the Thévenin equivalent circuit. I've shown you just a little bit of the theory behind it. And what we're going to do next time is I'm going to show you a way, well, how do you calculate VT given a circuit, or how do you calculate RT given a circuit? Then I can take that whole circuit and replace it with a single voltage source and a single series resistor. Okay, well, all right. So, but it looks like I'm about just a few seconds away from the end of class. So let's stop this here. In closing, don't forget there's an exam next week. It will be Wednesday. I will send out an announcement that describes the material that it covers, basically beginning of class through Thévenin equivalent circuits and maximum power transfer. You will have a homework due before that exam with solutions that you can look at, so you can see the work before the exam. Check out Slack. I've been having some discussions on Slack. If you have any questions, you want to get those to me in writing, or take a picture of your work or whatever, or describe it, post that to Slack. And thanks for joining class. I will start office hours in just a few seconds. So if you would like to join those, please stick around. If not, I'll see you next time. Have a great night.